Input-output types. Input-output can be performed in three fundamentally different ways: programmed I/O, interrupt-driven I/O, I/O using DMA. Programmed I/O is the simplest one, and we have the CPU do all the work. The steps in printing a string via a serial interface is given here. After the data printed is written by the user app into a buffer. The operating system usually copies the buffer with the string to an array, say P, in the kernel space, where it is more easily accessed because the kernel may have to change the memory map to get an user space. It then checks to see if the printer is currently available. If not, it waits until it is. As soon as the printer is available, the operating system copies the first character to the printer's data register, in this example using memory-mapped I/O. This action activates the printer. The character may not appear yet because some printers buffer a line or a page before printing anyway. Here in the figure, it is shown that first the user program writes the output into the buffer, then the buffer is copied into an array in the buffer area, then the information in the buffer is copied into an array in the kernel area, and then whatever inside this array is sent to the printer. So here we see whatever printed on the page. Here the code for copying from the buffer to the array P in the kernel area is shown. P is the kernel buffer. This is copy from user. Buffer P count. For I starting with 0, and while I is less than count, each time I is incremented by 1, this loop for on every character. Then we have a while loop here, while the content of the printer status register not equal to ready, it is waiting in the step. Loop until ready. Then the content of the printer data register is set as PI, output 1 character. Then return to user. Programmed input-output, simple, this is good, but tying up the CPU full-time until all the input-output is done. This is bad. This is acceptable, for example, if time to print a character is very short or CPU has nothing else to do. It is acceptable, for example, if time to print a character is very short or CPU has nothing else to do. In order to overcome the problems with programmed input-output, the interrupt-driven input-output may be used. The idea is that block the process which requests input-output and schedule another process. Return to calling process when input-output is completed. Printer generates interrupt when a character is printed, keeps printing until the end of the string. Calling process is then unblocked. An obvious disadvantage of interrupt-driven input-output is that an interrupt occurs on every character. Interrupts take time, so this scheme wastes a certain amount of CPU time. Here, the code for writing a string to the printer using interrupt-driven I/O is given. The process that asked for the string to be printed is blocked until the entire string has printed. In part A, the code executed at the time the print system call is made is given. First, copy from user, buffer P count. The content of the buffer is copied to P. Number of characters shown by count is copied. and then enable interrupts. Then, while the content of the printer status register not equal to ready, then wait here, and then when the printer is ready, the content of the printer data register is set as P0. Then the scheduler is called to continue with some another process. When the printer has printed the character and is prepared to accept the next one, it generates an interrupt. This interrupt stops the current process and saves its state. Then the printer interrupt service procedure is run. Here the interrupt service procedure for the printer is given. It is checked if count is equal to 0. If there are no more characters to print, the interrupt handler takes some action to unblock the user. Here, if count is equal to 0, unblock user. As the content of the printer data register is set as PI, count is decremented by 1, and I is incremented by 1. And then acknowledge interrupt, return from interrupt. Another solution is to use DMA, direct memory access. Use DMA controller to send characters to printer instead of using the CPU. CPU is only interrupted when the buffer is printed instead of when each character is printed. DMA is worth it if DMA controller can drive the device as fast as the CPU could drive it, and there is enough data to make it worthwhile. Here the code for printing a string using DMA is given. In part A, code executed when the print system call is made is given. Copy from user, buffer P, count is the number of characters to be printed as before, and whatever in buffer is copied into P by constraint count. Then set up DMA controller and call the scheduler to execute the next process. In part B, the interrupt service procedure is given. Acknowledge interrupt, unblock user, return from interrupt. In this figure, layers of the input-output software system is given. At the bottom, we have hardware. On top of it, we have interrupt handlers. Then we have device drivers, and then device-independent operating system software. At the top, we have user-level input-output software. Interrupt handlers. The driver starting the input-output blocks until input-output finishes and interrupt happens. The interrupt handler processes the interrupt and wakes up the driver when processing is finished. Drivers are kernel processes with their very own stacks, program counters, and states. Typical steps of hardware interrupt processing. Steps not listed here may also be required, and also the steps that do occur may be in different order on some machines. 1. Save registers, including PSW, this is program status word, not already saved by interrupt hardware to the process table. 2. Set up context for interrupt service procedure. 3. Set up a stack for the interrupt service procedure. 4. Acknowledge interrupt controller. If there is no centralized interrupt controller, in that case, re-enable interrupts. 5. Run interrupt service procedure. Extract information from interrupt and device controllers registers. 6. Choose which process to run next. 7. Set up the MMU, this is Memory Management Unit, context for process to run next. 8. Load new process registers, including its PSW. 9. start running the new process. Device drivers. Logical positioning of the device drivers, which are normally positioned below the rest of the operating system, is shown in the figure. In the user space, we have user programs, which become user processes when they are executed. And then we have kernel space. There we have the rest of the operating system, and inside we have printer driver, camcorder driver, for example, and CD-ROM driver. And they call the controllers for the hardware, which are, for example, printer controller, camcorder controller, CD-ROM controller. In reality, all communication between drivers and device controllers go over the bus. Driver contains code specific to the device. Drivers are supplied by manufacturer. They are installed in the kernel. However, user space might be a better place because bad driver can mess up kernel. It needs interface to the operating system for block and character device interfaces, and procedures which operating system call invokes the related driver. For example, read a block. The operations performed by a typical driver are as follows. It checks input parameters for validity. It makes abstract to concrete translation. For example, block number to cylinder, head, track and sector. Checks device status, might have to start it. Puts commands in device controllers registers. Driver blocks itself until interrupt arrives. It might returns data to caller and returns status information. Drivers should be re-entrant. That is, a running driver has to expect that it will be called a second time before the first call has completed. Device-independent input-output software. Although some of the input-output software is device-specific, other parts of it are device-independent. The functions of the device-independent input-output software are given here. For example, uniform interfacing for device drivers, buffering, error reporting, allocating and releasing dedicated devices, providing a device-independent block size. In part A, an operating system without a standard driver interface is given. Each device driver has a different interface to the operating system. Driver functions differ for different drivers. Kernel functions, which each driver needs, are different for different drivers. This needs too much work to have new interface for each new device type. Here in part A, an operating system without a standard driver interface is given. The driver interface is different for each device. For example, for SATA disk driver, we have such an interface, and for IDE disk driver, we have another one, and yet another one for the SCSI disk driver. However, for the operating system with an standard driver interface, all the disk driver interfaces are the same. If operating system is designed so that all drivers have the same interface, it becomes much easier to plug in a new driver providing it conforms to the driver interface. It also means that driver writers know what is expected of them. In practice, not all devices are absolutely identical, but usually there are only a small number of device types, and even these are generally almost the same. Interface driver functions. Operating system defines function for each class of devices, which it must supply. For example, read, write, turn on, turn off, etc. Driver has a table of pointers to functions. Operating system just needs table address to call the functions. Interface, names and protection. Operating system maps symbolic device names onto the right driver. In Unix, a symbolic device name, say for example, in the root directory device, and there we have disk 0. This maps to an inode which contains the major and minor device numbers. Major device number locates driver and minor device number passes parameters, for example, disk. For the protection, in Unix and Windows, devices appear as named objects. Then they can use file protection system. Buffering. Consider a process that wants to read data from an ADSL, asymmetric digital subscriber line modem, something many people use at home to connect to the internet. The case unbuffered input is shown in part A of the figure. One possible strategy for dealing with incoming characters is to have the user process do a read system call and block waiting for one character. Each arriving character can cause an interrupt. The interrupt service procedure hands the character to the user process and unblocks it. After putting the character somewhere, the process reads another character and blocks again. The problem is that user process has to be started up for every incoming character. In part B, buffering in user space is shown. Here the user process provides an character buffer in user space and does a read of n characters. The interrupt service procedure puts incoming characters in this buffer until it is completely full. Only then does it wakes up the user process. This scheme is far more efficient than the previous one, but it has a drawback. What happens if the buffer is paged out when a character arrives? The buffer could be locked in memory, but if many processes start locking pages in memory, then the pool of available pages will shrink and performance will degrade. In part C, buffering in kernel followed by copying to user space. Yet another approach is to create a buffer inside the kernel and have the interrupt handler put the characters there as shown in part C. When this buffer is full, the page with the user buffer is brought in if needed and the buffer copied there in one operation. This scheme is far more efficient. However, even this improved scheme suffers from a problem. What happens to characters that arrive while the page with the user buffer is being brought in from the disk? Since the buffer is full, there is no place to put them. In part D, double buffering in the kernel is shown in this part. A way out is to have a second kernel buffer after the first buffer fills up, but before it has been emptied, the second one is used as shown in D. When the second buffer fills up, it is available to be copied to the user, assuming the user has asked for it. While the second buffer is being copied to user space, the first one can be used for new characters. In this way, the two buffers take turns. While one is being copied to the user space, the other is accumulating new input. A buffering scheme like this is called double buffering. Instead of double buffering, a circular Queue of double buffers may be used also. Buffering is a widely used technique, but it has a downside as well. If data get buffered too many times, performance suffers. Consider, for example, the network given in the figure. Here, a user does a system call to write the network. The kernel copies the packet to a kernel buffer to allow the user to process immediately. It is shown in step 1 here. At this point, the user program can reuse the buffer. When the driver is called, it copies the packet to the controller for output. It is shown here in step 2. The reason it does not output to the wire directly from kernel memory is that once a packet transmission has been started, it must continue at a uniform speed. The driver cannot guarantee that it can get to memory at a uniform speed because DMA channels and also other input-output devices may be still in many cycles. Failing to get a word on time would ruin the packet. By buffering the packet inside the controller, this problem is avoided. After packet has been copied to the controller's internal buffer, it is copied out onto network. It is shown here as step 3. Bits arrive at the receiver shortly after being sent, so just after the last bit has been sent. That bit arrives at the receiver where the packet has been buffered in the controller. Next, the packet is copied to the receiver's kernel buffer. This is the step 4 shown in the figure. Finally, it is copied to the receiving process buffer, step 5 shown here. Usually, the receiver then sends back an acknowledgement. When the sender gets the acknowledgement, it is free to send the next packet. However, it should be clear that all this copying is going to slow down the transmission rate considerably because all the steps must happen sequentially. More functions of independent software. One of the functions is error reporting. When happens programming errors, the user asks for the wrong thing. The hardware problems, for example, bad disk, are reported if they can't be solved by the driver. Another function, it allocates and releases devices which can only be used by one user at a time. For example, CD-ROM players. It queues requests or lets open simply fail. Another function is device-independent block size. Operating system does not have to know the details of the devices. For example, combine sectors into blocks. User space, input-output software. Library routines are involved with input-output are printf, scanf, write, for example. These routines make system calls. Spooling systems keep track of device requests made by users. For example, think about printing. User generates file, puts it in a spooling directory, and daemon process monitors the directory and printing the user file. File transfers also use a spooling directory. An example flow through layers. User wants to read a block, asks the operating system for it. Device-independent software looks for block in cache. If not there, invokes the device driver to request block from disk. When transfer finishes, interrupt is generated. User processes is awakened and goes back to work. In this figure, the layers of the input-output system and the main functions of each layer is given. At the bottom, we have hardware. On top of it, we have interrupt handlers. Then we have device drivers. On top of it, we have device-independent software and user processes. When I/O is requested by the user process, it goes through device-independent software, device drivers, interrupt handlers, and hardware. After the request is completed, it returns back from the bottom layer, hardware layer, to the user process layer. This is the input-output reply. The input-output functions required are given here. Make input-output call, format input-output, spooling, etc. For device-independent software layer, we have naming, protection, blocking, buffering, allocation, etc. For device drivers, the input-output functions are set up device registers, check status, etc. For the interrupt handlers, the functions are wake up driver when input-output is completed, and for the hardware, perform input-output operation.